So I've been working on getting this motion blur effect working, and so far I've got it working on simple solid color, non-rounded rectangles, right? There's no outlining happening on them, so they're solidly filled. They're not gradients, they're one single color. There's no textures because they're one single color. And they're not using rounded rectangles, they're just straight up rectangles. So that highly oversimplifies the set of criteria I actually want in my renderer. But remember, this is actually all just to solve the problem of the thin rectangle. So at this point, where things are coming is I need to decide if I want to force this into one code path, which would have the benefits that I really like having things in one code path. I would then have access to effects like motion blurs on my rectangles of any size and shape and color. And on the other side, I might want to bifurcate this and have two different code paths. One that I specifically call when I'm drawing something that I know is supposed to work like a thin line so that it can use these effects. And then things like outlines and rounding don't make any sense in the case of a thin line. I might still want to figure out how to do a gradient. I might still want to figure out how to texture that, although it's not clear what exactly that would mean. It might still be useful. But you can see that there's like two different paths I might want to go down here. And I'm focusing on the single code path approach first for a couple of reasons. First and foremost, I have two different problems sort of at the same time. One is I have this question of what kind of effects can the pixels achieve at 60 frames per second, right? So I've picked the constraint of a sort of a pixel resolution, the color of colors available to those pixels, and then I've picked the constraint of 60 frames per second, and I need to figure out what kind of effect is even possible with those constraints. And if I also simultaneously try to think of what would be easy to compute, I might not have an answer to a more fundamental question, which is it even possible to make this thing look good no matter what? Like, is there a solution to what I'm looking for? Or does it turn out that there is not really a well-defined way to draw what I think I'm trying to draw? And this is just to clear up those ideas, right? What is the thing that would look good? How would it look if it was the best possible quality it could be? What kind of effects really are real and not just in your head? Once I know what kind of effects I could get out of the pixels, I could also pay some attention to the performance trade-offs of doing the full compute for a really complex solve that figures out how to color each pixel might not be ideal. So are you willing to give up a little bit of quality, or are you willing to not mix certain features together so that you can get the quality out of the use cases you do care about and get enough quality out of it that it serves its purpose well? And that's a second problem, and that has more to do with what can the GPU do, what can the CPU do, and how many of these things do I want to do per frame. But I don't want to think about that first if I don't have a clear answer in my head of what pixels could even give me as effects. So I'm focusing on one code path so that I can see what happens if I combine all of the features and try to solve it as well as possible. So to get started on that, I want to stick with what I've already been doing, which is computing exact pixel coverage. And I want to just see if I can extend that to rounded corners. So I'm going to go to the blackboard and do some math for a bit. It might turn out that this is so complicated that even doing it full accuracy on a first pass would actually be the wrong thing to do, but I don't know that yet because I haven't gone and explored the ways I might calculate the area there. So let's go and look at the blackboard first. Okay, so I think I've explored that thoroughly enough to satisfy me. I was looking at the case of an unconstrained circle, so any possible radius, against a square, which is enough constraint to capture what's going to happen when I look at, arbitrary circles going against pixels, because the pixels are going to be squares. But there's just too many options. There's too many ways that they can intersect and overlap, and it's fairly complex. There might be some kind of tricks in there I could use to slice those cases down a little bit more. I was thinking looking at each edge of the pixel as an infinite line and then clamping kinds of thoughts. So like find the intersection for the 1 or 2 points for each full vertical line that goes infinitely in each direction, and then using some sectors and some triangles and stuff. There's going to be a lot of angle calculations in that, possibly as many as 8 angles. just to handle one circle on one pixel, and then every square would have to do that. So every pixel near enough that circle that it gets hit by the original extended geometry. And of course, that's not even the full story. That was just for circles, which are a special case of rounded rectangle that more or less capture the interestingness of the rounded part, but there would be yet more work to do to figure out how to deal with a quarter circle and then the portion that's more rectangular and then this quarter circle again. And so one thing I could do to try to make this a little bit easier to deal with is to throw in a constraint, which is I don't think it's necessary for me to handle every possible radius. Unrounded rectangles, of course, are important, so I want to be able to handle a radius of 0, but that's super easy. I just don't do anything with circles. And then I could say once it's crossed over the radius of 2 or so, we could start actually applying it, but maybe in that range between 0 and 2, we just sort of apply a thresholding logic so that anything less than 2 acts like 0. It's not until about a radius of 2 that you get roundness that looks good, because at less than that you're dealing with roundness that looks more like fuzziness. A tiny little roundness on the edge there just means dim the corner pixels a little bit. And even if you get to a radius of 1 full pixel width, you're still touching all the same pixels, you're just touching them less. It's not until a radius of 2 that you're really hitting multiple pixels and could maybe see a shape of roundness emerging there. So I might take another crack at this with the new constraint that the box is considered a 1x1 box, which is a little more specific, and that the circle's radius is considered to be 2 or greater. That's going to remove some of the cases I have to think about, and maybe that will give me a shot. But if I don't think that that's very tenable after a little bit of exploration on that set of constraints, then I'm going to drop this and try to have to come up with a different way to test out combining these different visual effects. After exploring what's going on with that constraint, I'm starting to get some hope. There is still a lot of complexity. I have 7 different cases I have to detect, and I haven't quite convinced myself this is all of the cases, although I can't think of any other cases. I also haven't proven that this is all of the cases. So I, at some point, have to figure out how I would detect which case I'm in, and if I haven't got all the cases, then the fact that I'm missing one will kind of pop out there as a part of the code. There'll be a code path emerging. There'll be something I can detect that's not handled by any of my ideas yet, right? So I can kind of push that away for a moment, but I do have to deal with it. But immediately, the more important thing that's popping out at me is that I think I'm getting close to something that is actually computable. I do know how to compute the areas in all these cases if I throw out this sector triangle thing that is used to make these tiny little wedges. So the sector, just to be clear, is that pizza slice shape. And I don't actually usually want the full pizza slice. It turns out that what I'm usually getting is the pizza slice minus most of the pizza slice, the triangular part, just leaving in that little piece of the circle with the, you could call it the crust of the pizza slice, perhaps, right? That little area there I'm computing in every case. And when I think about it, the theta in those computations corresponds to how far apart the two intersection points are. So we have the circle intersecting with a pixel, and it's going to intersect usually in two places. In one case it's 4, but even then we use 2 of those as the predominant thing that adds area. And though the distance between those can't be very far apart, a lot of times it's going to be close to 1. It can get as far apart as square root of 2 if it goes all the way across the diagonal of a square, of a pixel, of a square-shaped pixel, right? But it can't get bigger than that. So there's an upper limit on how big the theta can be, and that makes the area of those sector wedges, the pizza crust shapes, those have to be very small. And so I might not be losing very much if I discard them. And all that's left after I discard those is a bunch of area computations based on squares and triangles, or trapezoids. Depending on how you look at it, it's a couple of rectangles, or it's a triangle and a couple of rectangles, or it's this very special pentagon in this case, but still built out of rectangles and triangles. So if it's going to be really easy stuff like that to compute, then I don't think it's too bad. It might even boil down to fewer cases if I figure out how the case detection works out, so that it's just, a triangle or a trapezoid or something like that gets me most of the area covered correctly. So I want to kind of explore this a little more. It's starting to feel promising. And what I'm going to do next is think through how I would detect each of these cases, because that's the piece I can't start without. If I figure out how I could detect each case and I become convinced that I've got a way to do it, I still don't have a great solution, because it's not ideal to have to detect one of 7 different cases on each pixel in a shader and then do these different computations. So it might turn out that it's not ideal, but at least it'll give me a pretty accurate idea of what this thing would look like if I did the fully accurate computation. And if it turns out that this is too much compute, then we can compare this result against something like a signed distance function that would be faster, or another approximation method. But I want to try this out first. I want to see if I can just ignore those little the pizza crust sections, and do the rest of this in a case-by-case basis and get a pretty accurate pixel coverage. Wow, this is getting even more encouraging. So looking at the simplest possible way I could think of to maybe create a test that can take each edge of a pixel and figure out if it's getting missed by the circle, covered by the circle, hit once by the circle, or hit twice by the circle. It kind of looks like I just stumbled into the next useful step of solving this problem. So by testing each endpoint, which was my idea, and looking at its distance from the circle, I figured maybe I could figure out if this point lies inside or outside of the circle pretty easily, and then classify the different types of edges just based on that. And that almost completely worked. So if I completely miss the circle, what'll happen is my edge remains completely outside of the circle forever, so the endpoints will both be outside of the circle. If I'm completely covered by the circle, then my endpoints will both be inside of the circle. If I'm only intersecting the circle once, so I have a single hit, then necessarily one endpoint is inside of the circle and the other one is outside of the circle. That's what it means to get hit once. And the only other case is getting hit twice. Now, for it to get hit twice, what that means is that it has to start outside of the circle, cross into it, and then end outside of it again. That way it has two intersections. I can't get two intersections any other way. But that's not the same thing as missing the circle exactly, but the test looks the same, right? If I test the endpoints in either case, I can't tell those two cases apart. However, what's interesting is if I just say, hey, let's pretend like the double hit case is the same thing as a miss, how bad of a sort of additional quality degradation happens there? And it turns out none. Because of the fact that I was already planning to throw away the pizza slices, the math of how I would compute the area turned into the same thing in both cases. Any case where I had a double hit, if I just instead looked at the miss case, the formula is exactly the same except for an additional pizza crust that was going to get thrown away anyway is usually present in the double hit case that is not present in the miss case. So what this means is that I'm not losing any quality at all by using this test after I've decided to throw away pizza crusts anyways. So I think that this is, again, a good sign of where I want to keep going. Now I have a way to test each point and use that to figure out for each edge, do I want to treat this as a miss, a hit, or a completely covered edge? And those will be the only three kinds of edges I have. But I still have some other problems. One problem is I need to compute the intersection point on the hits. So if you look at all the cases where I have a hit, sometimes it forms a triangle, sometimes it forms a trapezoid, and in this one weird case it forms like this pentagon made out of rectangles and triangles. But either way, I need to know the amount of area of that segment that is covered by the circle. So that's the last thing I need to be able to do. After that, I don't think it'll be a very efficient shader, but it'll at least be a shader that gives me a good idea of what this could look like. And then maybe I can do some more refinements to make it efficient enough to actually keep doing it this way. But let's not get ahead of ourselves. First things first, let me think of some way to calculate that amount of the segment that is covered on the hit case. All right, there are still some unknowns with this whole idea, but I think there's enough specificity here that I can switch to coding. So the first thing I'm going to do is transfer the ideas that are on the blackboard into some notes in ForCoder, and then I'm going to see if I can write a shader that does this. It might take a little while because I also have to set up sending down a circle with a center and a radius and all of that. And of course, I haven't even answered the question of how I'm going to turn that into a rounded rectangle later. So still some unanswered questions, but I want to see if I can get a circle looking nice using this technique first. Well, I'm pretty surprised by this, but that's looking really, really cool to me. I think I was expecting that the fully computing pixel coverage on a circle was going to be too much to ask for, but with just that little bit of shaving off the complexity on those, pizza crust shapes, as I was calling them, and then a little bit of organization in the code. Obviously, it was a super complicated fragment shader, but just a little bit of sort of structure there, and then some time spent debugging. It looks like I've got it working the way I expected, and it looks really cool. I don't know that this is ever going to be something I would use in a program I would ship. Certainly not in something that's going to run sort of real-time graphics like a UI. Seems like overkill for that. Maybe if I was trying to render really high fidelity shapes for, something like a video processing thing that could happen offline, I might use something like this. But even then, there's a lot of cleanup and improvements that I would probably do from this point. So now this kind of leaves me with an idea of where do I want to go next. I do want to try out signed distance functions still, because I think switching to signed distance functions is going to be necessary to easily get all of the speed I want and all the features I want simultaneously. But this gives me a really great case against which to test that, so I can see how bad is the sort of approximation of the signed distance function, or how good is it. I've never actually gotten a chance to look, so this is going to give me a way to, I could literally take the two and subtract them and have a difference that's like, yeah, the signed distance function does approximate circles really well, or it doesn't approximate them very well. So once I've got that, I also want to see how the signed distance function might be tweaked and improved to make the slow-moving thin line look good. And if that is possible, then we're kind of on our way to having a single code path that can do everything. What we have to actually see what those effects will look like and compare them against these kind of results that we're getting using pixel coverage, which is giving really nice looking anti-aliasing. So I think that's what we'll get started on next time, is trying out pixel coverage or trying out signed distance functions as a replacement for pixel coverage on each of the main things we've tried so far, and seeing how good or bad it is at recreating those effects in a sort of cheaper computational way.